Hello, this is problem set number 2, problem 2. A cylindrical tank has a tight-fitting piston that allows the volume of the tank to be changed. The tank originally contains 0.110 cubic meters of air at a pressure of 0.355 atm. The piston is slowly pulled out until the volume of the gas is increased to 0.39 cubic meters. If the temperature remains constant, what is the final value of pressure? Okay. So these two drawings are what the problem looks like. Initially, we have a cylindrical tank with a piston, right here. And we were given the initial values for the volume. So initially, V1 is equal to 0.110 cubic meters. And pressure, P1, is equal to 0.355 atm. Okay. The piston is slowly pulled out until the volume of the gas is increased to 0.39 cubic meters. So finally, we slowly pull the piston up, as you could see, right? We pulled this up, the piston, and it reached this point. And so the volume changed, it increased to 0.390 cubic meters. Okay. And we were also told that the temperature remains constant, so this is an isothermal process. So T1 is equal to T2. So T2 is equal to T1, right? So for that case, let's just call that T. So T1 equals T, T2 equals T, right? Because they're the same temperature. Temperature does not change. And we're looking for P2, the final pressure. All right. So let's use the ideal gas law equation, which is PV, the pressure, times volume is equal to the amount of gas, N, universal constant R, and temperature T. Okay? So I'll write this down in terms of initial and final state. Okay? So initial, I've got P1, I've got V1 is equal to N R T1, right? N1 R1 T1. And final, let's call it P2 V2 equals N2 R and T2. But we know that the cylindrical tank, it has a tight-fitting piston, right? So because it's a tight-fitting piston, I know that the amount of gas inside the piston won't change. So N is constant, right? N is going to be constant. Tight-fitting piston, N is constant because the amount of gas inside the piston doesn't change. Volume might change, pressure might change, but the amount of gas inside the piston does not change. Okay, so N is constant. R is constant because that's just the universal gas constant. So in that case, T is also constant, right? That was given right here. Temperature is also constant. So in that case, everything on this side, the right side of the equation, is equal. It doesn't change. So if that's the case, I'll just write that down. Use red. So right side of the equation is constant, or it doesn't change. right? So because of that, we can say that P1 V1 is equal to P2 V2, because these two things on the right side are equal to each other. They're constants. Okay. So I could just plug that in. P1 V1 equals P2 V2. And I am given the value for V1, so I know this. I'm given the value for P1, so I know this. And I'm given the value for V2, and I know that. And I am looking for P2, so I can solve for P2, right? Rearranging this, I would get P2 is equal to P1 V1 over V2. Okay? So I'll just plug that in. P1 is 0.355 ATM. V1 is 0.110 cubic meters. And that is all over V2, which is 0.390 cubic meters. Okay? And my units for cubic meters cancel out. And if I plug that in the calculator, I would get P2 is equal to 0.100 ATM. And that's my final answer. Okay, and that kind of makes sense because in this equation, PV equals nRT. So PV equals nRT, right? And we've established that this side of the equation is constant, doesn't change between initial to final. It does not change. So if that's the case, when here we see that volume was 0.110 cubic meters and it increased to 0.39 cubic meters. So volume, if volume increase and this stays the same, that means pressure has to decrease, right? And that makes sense. It was initially 0.355 ATM and it decreased to 0.100 ATM. All right, hope that helps.